In this video, I will explain the concept of chemical bonding. So before I get started, we're going to be looking at a very simplified view of bonding, just to give an introduction into what chemists do. But in brief, chemists are interested in creating and breaking chemical bonds to create new compounds, new chemicals that they want to do interesting things with. So first of all, a quick review. A chemical bond is between two atoms, and that forms a molecule. So remember, atoms are single elements found on the periodic table, like hydrogen, helium, lithium, beryllium, etc. It is just the atom is simply one of those elements. Now, a molecule is when there's two atoms that are interacting together to form the molecule. So that can be two hydrogen atoms, for example, to form H2, or it could be between any other atoms found on the periodic table. In addition, the molecule can be heteronuclear, meaning that the two atoms that are interacting are not the same. So, for example, you could have a hydrogen atom and a fluorine atom interact to make a HF bond. That is also possible, and that's also a molecule. So the key thing to remember is that a molecule is composed of two or more atoms. It could have many, but it has to have at least two. If it's just a single atom, then it's just an atom. It is not called a molecule. So the interaction that holds the two atoms together in the molecule is called the bond, and that's what we're interested in this video. So while that's all fine and good, it doesn't explain why the bond does form in the first place. And to understand that, we need to use a little bit of physics. Specifically, Coulombs Law explains this phenomenon. And just so you know, the Coulombs Law comes up time and time again in chemistry, and it's a fundamental principle that you need to understand, and it can be applied to many chemical concepts. So it's very good to have a solid grasp on Coulombs Law before you move forward with any other chemistry. So in words, Coulombs Law is simply that opposite charges attract one another and like charges repel one another. So in a chemical context, we have positively charged protons and negatively charged electrons. So the interaction between a proton and electron is attractive because the charges are opposite. However, if you had two protons near one another, they would repel because they have the same positive charge. Similarly with electrons, if there's two electrons near one another, they would repel because, again, they have like charges. Now, you can specifically define the Coulombs Law in an equation, which is more for physics, and sometimes it'll come up in chemistry, but it allows you to quantify specifically what the interaction is, whether attractive or repulsive, but you can find the specific value of that attraction, which is good to determine what type of interactions are most favorable or least favorable. So before I move on from that, favorable just means lowest energy or lowest force, and unfavorable means higher energy or higher force, since it requires the input to cause the change to the state, whatever we're talking about. So specifically looking at this equation, we have many undefined things here. First is F, which is the Coulombic attraction or repulsion, typically in terms of force, but this will also be used as energy later, that we'll see in the next part here. In addition, we have K, which is Coulomb's constant. That's just an experimentally found value that doesn't have any bearings on what we're talking about here in terms of the attraction or repulsion. Q1 and Q2 are just the charges of specific particles. So for example, in our context, we have protons, that would be +1, and electrons would be -1. Now, they do have specific charge values and expressed in the unit of Coulomb, but we're not going to talk about that here. We just want to understand the basics. And then R is the distance between the charges, which is typically in meters or some unit of that like. So if we consider a specific example of two protons interacting, and we use this equation to determine the value, or at least the sign of the resulting vector, we can determine if it's attractive or repulsive. So first, we know K is just a positive integer. We're not concerned specifically with the value. We know that protons are both positively charged, so Q1 is 1, Q2 is 1, and then the distance between them is also just a positive value that will be defined depending on the context of the situation that would be proposed. So in summary, K is positive, Q1 and Q2 are positive, R is also positive, so this must be a positive value. A positive force means that there is a repulsive force because you have to input that energy to force the interaction, or input that force in this case to cause that interaction. If you considered a proton and electron, Q1 would be positive, Q2 would be negative. For example, again, K and R are both positive, so this value would be negative. So what that means is you need to lose force or lose energy in order for that interaction to occur, which is favorable. And as I said earlier, it's just in simple terms, it's the lower that value is, force or energy, the more favorable that situation is, that outcome would be. So with that, we can now define that using Coulombs law, whether an interaction is attractive or repulsive based on the sign, and we could also explicitly find the strength of that attraction or repulsion based on just plugging in all of these constants that we have here, K, Q1, Q2, and R, depending on the situation. So now, if we consider a generic example of two hydrogen atoms specifically coming together, as they're approaching one another, we will see that the protons of the first hydrogen atom will have an attractive force with the electrons of the second hydrogen atom, and this will be a negative in our force value, and we'll just call it F1, but that is an attractive force. Similarly, the electrons of hydrogen 1 and the protons of hydrogen 2 will have the exact same type of interaction. Now, keep in mind that as these are approaching one another, the protons of hydrogen 1 and the protons of hydrogen 2 will be repelling one another, which would make an unfavorable situation. Same with the electrons. As the atoms are getting closer, the electrons are also getting closer to each other, which would cause a repulsive force also, which would be positive. And also keep in mind that the protons and electrons within the atoms are still interacting to one another, not necessarily between the atoms. Just this proton and this electron, this proton and this electron also have positive forces, attractive forces that I'm not talking about here, or not showing in this diagram, because it would just mess up the figure. But you need to remember that that is happening, and that takes away some of the strength of this attractive interaction between the protons and electrons. This suggests that there is a perfect distance in which the attractive forces overcome the repulsive forces, creating an energetic minimum for which the attractive forces are the strongest, leading to the lowest energy state that's possible. So to find this particular energy minimum and the distance that it creates the energetic minimum, you need to use the Coulombs Law equation and find varying values for energy at different points of R for the electron-proton case that we have here. What results is the following figure. This is the Morse potential. We'll get into a little bit what the Morse potential is specifically in a later video, but here, this is essentially what we have in the Morse potential. So to interpret this figure, we see the x-axis is R, which, as we described before, is simply the distance between the atoms, and E is the Coulombic energy. So in this context, we're just going to say that force and energy are essentially the same here. There are differences, and especially if you're going to get into physics and physical chemistry, you'll need to know the differences, but here you can equate the force to energy for this purpose. The next thing to point out is this zero energy state here, indicated by the blue dotted line. That is important because anything above this is where energy is absorbed by the system, so forcing a higher energy state. That's why it's positive. Anything below that is releasing that energy, causing a lower energy state. So one thing to mention before we interpret this further is that nature is always looking for the lowest energy state possible. The lower the energy, the less you need to input into that system to cause that state to occur. So for example, if we go from out here where there's no interaction, zero energy. Down here, we're releasing this amount of energy to the surroundings, causing this to be a lower energy state. Nature is always going to prefer the lowest energy state that's possible, so this is going to be the state that this molecule exists in, because it's much lower than all the other possibilities. And again, since that energy can't just disappear, since this is lower in energy than this state, what the difference between these two, it means that this state, between the transition between this state and this state, must cause a release in energy that's equal to the difference between this point and then wherever we started here at this point. So now that's good. And again, we're always looking for the lowest energy state. To interpret this graph a little bit further, the easiest place to start is where R is very large, or R is approaching infinity, because at that point, if we consider our equation again, R squared is getting very, very large. When that gets very, very large, the force goes to zero. Since this denominator gets larger, it drives all of this to zero. And that's why in our graph, we see it asymptotically going to zero, because as R is getting bigger and bigger, this is getting closer and closer to zero. As R gets a little bit smaller, away from infinity, we start to have the attractive forces that I talked about earlier. These attractive forces will start to cause some kind of weak interaction that we don't necessarily call a bond yet, because it's not the minimum energy state, but it is starting to decrease. And again, the energy difference between this state and this state must be the same, or must be released to cause the same overall energy. There's no change to the energy. It's not created or destroyed. And then again, you keep moving closer, move the atoms closer and closer to each other until you reach an energy minimum, where the attractive forces are as strong as they can possibly be, and the repulsive forces are still there, as I talked about before, but they're at the minimum that they can be. They are being dominated by the attractive forces. They're not driving the energy up at this point. And this bond distance can be measured experimentally and then verify that this graph describes what we're talking about, or the specific atoms that we're talking about, but this is the energy minimum, and this is always where the atoms are going to exist because the attractive forces are greatest. Then if you move a little bit closer, beyond the closer than the bond distance, the repulsive forces begin to dominate, and at that point you start to increase in energy, because the repulsive forces will cause them to separate a little bit more than the bond distance would. And again, you keep moving smaller and smaller R, and eventually you cross our threshold here of releasing energy to absorbing energy, and this state really isn't going to occur because it requires an immense amount of energy to be input to the system to cause this state to exist. And like I mentioned earlier, nature is always looking for the least energy state that's possible. So this bond distance is where the atoms or where the molecule is most likely going to exist, because it's the easiest state, it's the less resistive. So, however, though, should mention these are possible to exist, but it must be in extremely high energy states, like particle accelerators or stellar supernova or anything like that. The last thing I should mention is this entire picture is describing a covalent interaction in which the electrons are still associated with the atom that they started with. There's no transfer of electrons. So what this means is that the electrons are effectively being shared between the two atoms, since there's no transfer occurring. And because of that, there is still all of the same interactions within one atom. So the electrons of hydrogen 1 are still being attracted to the protons of hydrogen 1, and same for hydrogen 2. So what that does is effectively pull some of the attractive forces away from the bond that we want, the inter-atomic interaction, in which the protons of hydrogen 1 and electrons of hydrogen 2 interact to form the bond. So because of that, it makes covalent bonding a little bit weaker than the other alternative that we'll talk about now, which is ionic bonding. Ionic bonding involves a transfer of the electrons, in which, again, the two atoms come close to one another, but one of the electrons from hydrogen 1 will be transferred to hydrogen 2, for example. Again, I'm just using hydrogen as an example. You could do this with many atoms. So the net result of this kind of transfer is these atoms here. So this is hydrogen 1. The only difference is it's lost that electron, and it's been donated to the hydrogen 2. Now notice I bracketed the entire atom because there's now a localized positive charge on this atom because the electron is no longer present to balance the positive charge of the proton. And similarly, the second hydrogen atom that's gained the electron now has an overall -1 charge because we have 2 electrons and 1 proton, so that is 1 minus 2, -1. So overall, this has a localized negative charge on this atom. Now, the interaction that occurs here is, again, still between the protons and electrons of this atom, but however, it's a much stronger interaction because we don't have the atomic attraction that pulls the bond in multiple directions. Since it's gone here, it's simply just a proton and electron interaction, and that is much stronger than the covalent type that we described earlier. Do note that there is still proton-electron interaction within the new atom here, but it doesn't take away from the bond because it's not shared between both of the atoms. And the last thing to point out here is the atom that donates the electron we call a cation. We call positively charged ions cations just by definition to distinguish the two. So the one that donated electrons becomes the cation. This is specifically H+, because it is now a hydrogen atom that has a positive charge because it's lost that electron. And the atom that has gained the electron is called the anion. Again, just by definition, negatively charged ions are called anions, and this now has that localized negative charge, so this would be H-. Specifically, H+ we just refer to as a proton because it is simply a proton with a neutron and no electrons, and this we call a hydride. We'll talk about that a little bit more later, but it is just the hydrogen atom with 2 electrons. So with that, I hope you benefited from this video and learned something. If you did, please hit the like button. And if you want to find your way back to the channel, please hit the subscribe button with the notifications on. And with that, I hope you have a great day, and I'll see you in the next video.